All right, so today we're going to take a look at section 8.5, which is partial fractions. And in order to do partial fractions, I'm kind of just going to give you some step-by-step ideas of things to think about in different situations. The first issue is that we're going to talk about the numerator being n of x and the denominator being d of x. And the first thing we need to do is if your numerator is larger than your denominator, that is the degree is larger, then you need to use long division. Okay? So that's definitely an algebra topic you probably haven't used in a while, unless you've used it real recently with integration, and you might have, but we're going to use this division idea. As long as your degree on top is smaller than the degree on bottom, the next thing you do is you factor the denominator. Then you'll write your denominator as a summation of fractions so that each of the denominators has one of the different factors as its denominator. That's where the factors are coming from part 2. You're going to write each numerator with a degree 1 less than the denominator. And then you're going to reconcile the created summations with the original fraction. And I put a note on here that up until the point that you actually do the integration, which you notice was not any one of those steps, right? Every step was what you do before you integrate. All of those steps up there are actually college algebra topics. And I've tutored a girl in college algebra once, exactly once, where she covered this topic in college algebra. It is very uncommon because it's one of those ones that, it's one of those things that if you get to it at the end, that's great. But it's not a topic that we tend to get to at the end because we've got other things we try to get to before then. So it is a college algebra topic, all right? So we're going to take a look at the first example. You'll notice that denominator, 4x squared minus 1, and you've got your numerator of 1, and it sort of looks like a property or a different integration you've seen before. It looks kind of like what? Do you recognize it? It looks like you might deal with some with natural logs or with what else? Trigonometric functions. It has sort of that feel to it because the trigonometric functions have this sort of a thing in the denominator. But with the trigonometry, there's not one that matches up exactly to this form. So we're left wondering, what do we do with that now? So let's take a look back, and you've got it right on your screen. The first step over here was to do the division if we need to. But my degree of my numerator, do you know what the degree of this numerator it is? It's 0. The numerator, not the denominator, the numerator on top. Right? It's got a 1 up there, so its exponent would be like x to the 0 for the power for a value of 1. Okay, so no exponent or no exponent on top or an exponent of 0 on top, and then the degree of the denominator is 2. So my degree of my denominator is already larger. Does that make sense so far? Okay, so we don't have to do step 1. That's good. Step 2 said, what am I supposed to do? Factor. All right, so we're going to do a little test of seeing how well you guys remember how to factor. Do you know how to factor that guy? It is. Can you tell me what you get?
2x plus 1, 2x minus 1.
Good. 2x plus 1 and 2x minus 1. So, yes, I picked one automatically that factored really nice and clean, and you guys would remember that form. Okay, so that's one of them. All right, so that's step 2. We just did it. Can you manage that step? Factoring, right? All right, so step 3 is that we're going to sort of separate this. And we separate this with addition because it said I'm supposed to do a summation. So what does that mean? Well, it means I'm going to have one denominator that's one of those factors, and I'm going to have my other denominator that's the other factor. And later on when we get to example 2, you'll see that we may have more than 2 fractions even, and that's okay too. But something's missing, right? I don't have any numerators written down, and the numerators are not both 1. So what do I do next? Well, what you're going to do is you're going to write the numerators that have degree 1 less than the denominator. So let's talk a second. What's the degree of those denominators? They're 1, right? So the numerators should have degree 0. So the numerators are just going to be constants. There are going to be some number on top of each of them. Agreed? But we don't know for sure what number goes there. So what we're going to put there for now is we're going to put
A and B. And we're going to recognize that the A and the B, and whatever we have more, C's and D's and whatever, these are just different numbers that we have to figure out what the numbers need to be. And trial and error, probably not the best method for doing so. Okay? You might get lucky occasionally. In general, you're going to be at it a while if you try some trial and error. So what are we going to do? Well, if you take a look at step 5, what did step 5 say I need to do? Right. Reconcile that current summation with the original. What does that mean? Well, what it means is I'm actually going to take these two fractions that are currently separated with addition, and I'm going to put them back together by adding those two fractions together. So tell me what you remember about adding fractions. That's definitely a pre-college algebra topic right there. What do you have to do in order to add fractions? You need a same denominator, and these don't have them, do they? So what am I going to do? Yeah, I'm going to get a common denominator by cross-multiplying or multiplying them together. And in order to multiply them together, I actually need to multiply the tops and bottoms of each fraction by different values. Let's go with blue. So the first fraction needs to be multiplied by 2x minus 1. And the second fraction multiplied by 2x plus 1. And if I do that to a denominator of a fraction, I'm doing it also to the numerator of the fraction, right? All right, so what I have now is I have what looks to be a much bigger mess than I had before, doesn't it? Yeah. All right, so I have a times 2x, well, that's 2ax, minus a times 1, so minus a, plus, and then b times 2x, so that's 2bx, and b times 1, that's plus b. And then the denominator is the same denominator I started with in factored form. 2x plus 1 and 2x minus 1. Okay, again, we're not doing anything that's beyond algebra at this point, but it may have been a while since you have algebra, so if you have a question, you should ask. This is okay, except for the fact that it looks like more of a mess than I started with. Okay, now, one of the things that you will remember from working with fractions is that when you have two fractions that have the denominators that are equal, if the fractions are equal, what do you have to say about the numerators? They're equal too, right? So whatever this mess of a numerator is that I've got right now, we know what it's equal to. It's equal to 1. Everybody good with that? Okay, so what I'm going to do right now is I'm sort of going to take an aside. I'm going to actually, what do I want to do? I'll do it on the next slide. I'm going to take that 2ax minus a plus 2bx plus b, and I know it's equal to 1. My goal is to figure out what in the world a and b are. Because if I can figure out what a and b are, I can go back to this fraction over here that I had, that second line before I multiplied those common denominators together, and I'll have actually broken it into two simpler fractions. Does that make sense? So if I could figure out what a and b are, I would be well on my way to making the problem work for me. So we're going to take a look at doing that. Now, in order for all of this to be equal to 1, what you notice is that that 1 doesn't have any variable x in it, right? So I actually could write this as something like that. There's no x's. There's 0 x's. Okay. I want to actually collect terms. Now, I know that whatever x equals on the left, it has to be the same value times x on the right. So these pieces that have x in them, here and here, they have to equal the 0x on the right because they're all multiples of x. Are you guys with me on that? And the same is true for my constants. This negative a, this positive b, and this 0, those have to somehow, you know, the negative a and the positive b, those have to combine to be equal to the 1. All right, so we're going to collect them and write them like this. So this is my x term, and this is going to be my number term. I'm avoiding writing a c for a constant because I'm going to need c for something else later. So I don't want to confuse you with too many c's on the page, okay? All right, so my x's. Well, my x terms, on the left side, I've got 2a times x, but it's 2a. That's the x term. And I've got 2b as an x term. And on the right-hand side, I have a 0. So I'm doing all the comparison of the variable x in one line, one equation. And then I'm going to do all the comparison of the numbers in the next equation. So I'm going to have negative a, I'm going to have positive b, and I know that that has to equal the number 1. Okay, so far so good. That looks like a system of equations, doesn't it? Another algebra topic. Okay, you're going to have so much fun with algebra today, it's just unbelievable. All right, how do you solve when you've got something like this? You've got lots of options, so somebody give me one. Good, so substitution is one way to do that, and it would work pretty well with this one, wouldn't it? Because that second equation, I don't have coefficients in front of a or b to work with, so that'd be a great way to do this one. What's another option if you didn't want that or didn't like it or something? Elimination is another option. This one's kind of set up so that the elimination seems natural because the a's are lined up in front of the b's and so forth. So either way's fine. Which one do you guys want to see? You can do substitution. Okay, so let's do substitution. I'll take my second equation and let's solve it for b. What does b equal? 1 plus a. All right, so b is 1 plus a. So then what do? Plug it into where? The top one. Okay, so my top equation now has a 2a, and it should have had a 2b, but it's now going to have a 2 times this 1 plus a, which is our equivalent value for it. And all of this equals 0. Excellent. So now that's good because I'm down to one variable and I can solve for it. So I have 2a plus 2 plus 2a equals 0. Now what? Somebody said 2 plus 4a equals 0. Then what? 4a is negative 2. So what is a? A is negative 1/2. Sorry, my negative's not very large. Let's try that again. All right. A is negative 1/2. What's b? It's 1 plus that. So what is 1 plus negative 1/2? It's 1/2. So my a and my b are both values that are fractions in this case. Okay? That happens sometimes. It's okay. But what that does for me over here is that allows me to take this step right here and rewrite it where things are separated. So was a the negative one or the positive one? Negative. Okay, so a is negative 1/2 over 2x plus 1. And, well, let me go ahead and write dx here and we'll separate them. And then the b is the 1/2, right? Over 2x minus 1. Now, it's perfectly fine to leave those fractions of 1/2 and negative 1/2 in the numerator. If they're really bothering you, what could you do instead? You could multiply the denominator through by 2. There's something else you could do too. You could put it outside the integral and the very front of it. So if you didn't want to see it sort of inside the problem as though you're working with it right now, you could deal with it at the very end. Okay, and that's actually how I usually deal with it. So is it okay with you if I do that now? Okay. So I'm going to write mine as negative 1/2 times the integral of 1 over 2x plus 1 dx plus 1/2 times the integral of 1 over 2x minus 1 dx. All right, give myself some more space here. All right, so this is what we're working with, right? Did it all copy okay? I think it's all there. All right, so we actually can integrate that now. Those denominators are integrable. So what do you see them as being? How do you integrate 1 over 2x plus 1 or minus 1? You can use natural logs, right? Now, there's some substitution in there. If you would like to see it, I'll show you once, just because I'm not sure what all you guys have seen and how recently. So I'm going to show it in case you would like to see that. I'll do it on one of them. You can actually be the 2x plus 1 In which case, what's du? 2 dx, right? So right now I can replace the integral from right here with 1 over u, almost. What do I have to do to compensate since I had a derivative of u like that? I need to make this 2 on the other side, right? I need to divide by another 2. I already have a 1/2, a negative 1/2 out in front, so what can it become? Negative 1/4. All right, so here's negative 1/4 out in front. Again, negative 1/2 of that is from the original problem, and then another 1/2 of that's from that derivative where I did the u substitution portion. Okay, does that make sense? You guys okay with that? Or do we like u substitution? Okay, good. All right, now the other piece is going to work the same way, right? Even though it's 2x minus 1, it has the same u du, and it would all work exactly the same way, agreed? So if I take that and deal with it this way, I could actually rewrite this then also as 1/4 integral of 1 over u du. Okay, I should operate without a different letter because it's not actually the same u. Let me fix that. I'll use v. I don't want you to think you can combine them because they're not the same. They just have the same derivative. Okay, so let's use some integration now. That's what we're doing. This is calculus, right? All right, so we have negative 1/4. What is the integral of 1 over u? That is the natural log of, there we go, absolute value. Just make sure I heard it. Absolute value of u plus the 1/4 natural log, the absolute value of v. Good, plus c. Awesome. All right, and then I'm going to put my u and my v back in there, right? So this is negative 1/4 natural log of what? And plus 1/4 natural log of what? 2x minus 1. I'm running out of space. We'll see if I have another screen. And you know, the calculus of what you've done is really done now. I mean, you found the integral. That's great. I guarantee if you look in the back of the book, and probably if Dr. Nichols were here telling you, he'd tell you can't leave it that way. Any idea of how you might simplify that result?
Put everything over 4.
What's that?
Put everything over 4.
You could put everything in 4. Let me actually, now that's one way to deal with it. I'm not thinking, yeah, I've got more space. Here, let me move this to the next screen. Okay, that wasn't what I wanted to do. All right, well, there it is anyway. Okay, so we could put everything over 4. Let me do that, and then I'll show you something else that we can think about after we deal with it from that way, because that's a good place for us to start. So this is actually negative natural log of 2x plus 1 plus the natural log of 2x minus 1 all over 4, right? Okay, so let's look at the numerator. What can you do to simplify the numerator?
Can you combine the two natural logs?
You can. Do you remember how?
You have the natural log of 2x minus 1 over 2x plus 1.
Right. So there's a property for natural logs that if they're subtracted, they can be combined with division, right? At least the interiors of them can be combined with division. And this is subtraction because at the very front here, there is that negative sign going on. So I do have a subtraction even though the sign between them technically at the moment looks like addition. So this is natural log, and it is an absolute value. You can either write the absolute value over the absolute value. You can just put absolute values around the whole thing. So I'm going to do that way. And then I have the 2x minus 1 on top and the 2x plus 1 on bottom. Is that all right so far? I'm going to put the 1/4 back in front because there's one other thing with logs that I could do with it. Do you remember? Yeah, it can be written as a power. What is a power of 1/4? It's a 4th root. So I can take this and make it an exponent right here, and this exponent's actually a 4th root. 2x minus 1 over 2x plus 1. We probably should still have absolute value signs in there because we do need them. In fact, we absolutely need them now, pun intended, because we need that to be positive in order to take a fourth root, don't we? Yeah. And then plus c. So this is our final result that looks nothing like the original result that original problem we started with, does it? Okay, now if I tell you they're not all that hard, will you be okay with me doing another one? Okay. They're not all that hard. What I wanted you to see from that one is this sort of natural progression of being able to split things apart and look at them. The splitting things apart on the next one's a little bit different, but the algebra at the end's a lot cleaner. Okay? So let's take a look at the second problem. All right, so taking a look at this one, degree of the top is 2. The degree of the denominator is 3. So I don't need any long division on this either, right? Okay, in fact, I'm thinking that I'm letting Dr. Nichols deal with the long division later. So taking a look at this one, I don't need to do step 1. I'm going to start with step 2, and step 2 says I should do what? Factor the denominator. All right, so you guys tell me, how do I factor this denominator? Good. X squared times x plus 1. Thank you. Good. And as I take a look at it from that perspective then, it looks like there's 2 pieces that are in the denominator, doesn't it? I mean, I've got an x squared and I've got an x plus 1. I contend there's 3 possible denominators there, though, and let me show you what they are. Some of you are nodding. You already know. Awesome. So I'm going to, let me rewrite this numerator. This is 4x squared plus 2x minus 1. So one denominator possible is actually the one I'm going to start with, the one you may not have seen, is actually a denominator of x. If you had a denominator of just plain old x, it could still be multiplied by the result of another 1 over x to give me the x squared component. I also have a denominator that's going to be, I shouldn't have written 1 on top, I'm sorry, let's fix that, over x. I also have a denominator that can be over x squared. And then I have a third denominator that's actually going to be the x plus 1. Okay, so the algebra on the front end of this looks a little bit weird. But the rule of thumb is I need to be able to say that when I multiply these back together and get a common denominator, the common denominator for all 3 of these would be the original denominator I started with. And would it? Yes, right? I mean, if I try to get a common denominator here, it's perfectly fine that one of the denominators started out as x. I can turn it into a denominator that's x squared times x plus 1. So anytime you have a power on one of your denominator pieces, one of your denominator factors, you have to use both that value without the power and the value with the power as potential separate fractions. Okay? So let's keep going and you'll see what will happen. Now it said back in the rules or whatever that I need my denominator or my numerators to have 1 less power than the denominator, right? So we've already dealt with the case like the first one where it's an x and the last one where it's x plus 1. Those both have degree 1, right? So those numerators would just be some constant. So it would be a, and I'm going to put at the back here c, and we'll talk about y in a minute. Now, when I have that duplicated denominator thing going on is the one time when my rule number 3 or whatever I wrote down for you, it is not right. You actually can stick with that same level of denominator or numerator you had before. Now, I know that doesn't exactly make sense, and you're thinking, well, okay, fine, put a b there, but we'll see in a moment why that will actually not be the case in general. But the reason that I'm able to put a linear or a constant term there is because that duplicated denominator issue going on. I've got an x, I've got an x squared, so I can just write that numerator as a single value b. Okay. Yes?
If it was x cubed instead of x squared, would it be the same?
Well, if it was x cubed instead of x squared, you would have had an x and an x squared and an x cubed for your 3 denominators, and you'd still have constants on top of all 3 of them. Now, let's say, for instance, we factored this denominator, and we'll get to one here in a second that has this sort of a flavor to it. And one of the features of the denominator, instead of it saying, let's say instead of it saying x plus 1 at the end, it said x squared plus 1. Okay, so is everybody with me? Just pretend that last denominator said x squared. Well, x squared plus 1 doesn't factor, not in the real numbers. So x squared plus 1 is exactly the best factoring option I've got. but then it would be a power of 2 in the denominator, a legitimate power of 2 that's not a repeat like this one is. Are you with me? So instead of just having c in that numerator, I would need a linear term in the numerator because it's a quadratic in the denominator, power 2. So over the side here, let me show you what would happen without messing up the one I'm working with. If I had that x squared plus 1 as my denominator, I would have cx plus d as my numerator because that's a linear equation like y equal mx plus b over a quadratic expression. Okay? We're going to do on part number 3, the problem number 3 you have in the sheet actually has one that's like this on there. Okay, so you'll see that happen in a minute. I don't have that going on here, however, because I've got this repeated x and x squared with one of them being a factor of the other one. So I won't need that. Okay, what am I supposed to do next now that I've got these a's and b's and things? Common denominator. So what will I need to multiply the first value or the first denominator by? Oops. Just going to move this over here a little bit. All right, so I can multiply the first one by not x squared times x plus 1, but x times x plus 1. Because I've already got one of the x's there, so if I multiply it simply by one more x, I'll get the x squared. Okay, that will make the denominator originally what it was originally. How about the second one? What does it need to be multiplied by? X plus 1. And how about the last one? What is it? By x squared, right. Okay, everybody got the sense of how that works then? Because that's an important piece of that. All right, so now we're actually going to multiply this out. I've got ax squared plus ax, that's my first one. In the middle, I have bx plus b. And at the end, I have cx squared. Does that look okay? There's an error on my paper. That's okay. All right, and then the denominator would be this x squared times x plus 1. Yeah. Okay. All right, is that all right? We're all good? Sorry, my paper's just got errors on it. All right, so we're going to take that numerator, and that numerator has to be, whoops, that numerator has to be done with, just like on the last one, what happens. So we'll use another slide. And all this is supposed to equal what? Right, 4x squared plus 2x minus 1. So we're going to collect terms just like we did last time. The first term we're going to collect is the x squared terms. So everything that has x squared in it gets collected from both sides. And I'm going to write all the pieces as though they do not have the x squared with them because they're all comparing one another. They're compared to one another. So I've got a plus c equals 4. Is that good so far? Great. All right, next one, the x terms. I've got a couple of them on the left and one of them on the right. So this one is a plus b equals 2. And then I've got my constant terms, and this is why I didn't want to use c for constant and why I'm using a number sign instead. I've already got a c in the problem, right? And then I've got this b and this negative 1. And that's actually fabulous. Why? Yeah, I mean, how nice is that, right? I don't even really have to use much, I don't really have to use systems of equation exactly to do that, right? No substitution or elimination. All right, so b is negative 1, that's great. So then the a, so what would a be then? A will be 3, and c will be 1. And I don't have any fractions even, do I? I don't know about you guys, but fractions are sometimes not the easiest to work with inside of a problem, so that's kind of nice. All right, so b is negative 1, c is 1, and a is 3. All right, so coming back over to my original slide where I was working the problem, I had a as 3. So this is 3 over x dx. I'm going to go ahead and separate them. The b value is negative 1, so you can put the negative 1 out front to make it negative, or you can put it on top. And then this is over x squared. And then I've got my c value. Oops, I left the dx off. Let's try that again. My c value was 1. All right, so now we're doing calculus. Now we're integrating. What are you going to get? What's the first one? Good. I don't even need any u substitution. 3 natural log of x. And there's my absolute values. What about in the middle? Are natural logs going to be involved in the middle one? No. How do you know? Because it's x squared. The power in the denominator is not a linear term, right? It's not a linear exponent. So this isn't going to work with logs. So now what? Good. So I could rewrite this as, in fact, I'll put the negative in front. And I can rewrite this as maybe like x to the negative 2, right? And then you can use your power rule. Yeah? So what does your power rule tell you that this one's going to be? X to the negative 1 over negative 1. There's lots of negatives there. We'll fix that in a minute. How about that last one, 1 over x plus 1? Yeah, that's a natural log one. Natural log of what? Yeah, absolute value of x plus 1. Okay, so I've got 2 natural logs, so those can definitely be combined, much like they could have in my previous example problem, right? So here's what we're working with. So this piece right here and this piece can be combined, but I got something different going on than happened last time. What's different? I mean, I can't just combine these together exactly yet. There's a coefficient on one of them, but not the other one, right? And I sort of eliminated those 1/4 coefficients by making it a denominator. Somebody had suggested doing that last time. How am I going to eliminate this exponent, or this coefficient, this 3? I'm going to make it an exponent, right? So I'm going to actually deal with this one as natural log. You can put the exponent inside or outside. It doesn't actually end up making any difference. Mathematically, it'll be the same quantity. While we are here in the middle, what can be combined, or what can be simplified by negative x to the negative 1 over negative 1? Yeah, plus 1 over x. Much nicer. And then I've got my natural log of absolute value of x plus 1 at the end, and I've left something off. I need a plus c. We'll get that back in there. We'll even fix it over here. Okay, so then I can combine the natural logs. How? With multiplication, right? Because these are added together this time. So I've got the natural log of, and I'll write this as the absolute value of x cubed times x plus 1. I can't combine the 1 over x with it, however. It doesn't have any logs involved, so he's just at the end, and then plus c. Okay, is that all right? Making sense? Okay, we have one more example. All right, this one doesn't even hardly look like a denominator I have to do much with to factor, but I can reduce it differently. That is, I can split it apart into the 2 fractions. Before I do that, let's actually notice what the degrees are, just as a cautionary statement. What's the degree on top?
2.
It's 2. What's the degree on bottom? It's 4. Everybody see that? I've got a power of 2 inside, raise the 2 on the outside. Okay, good. So I don't need to deal with step number 1. We'll just let Dr. Nichols deal with that on Monday. But we're going to deal with step number 2, which is just to separate these fractions. But like I said, they kind of almost don't look like there are 2 fractions. So you tell me, what are my 2 fractions? What are the denominators of them? Got x squared plus 9. And what else? Yeah, like the original one, right? X squared plus 9 squared. I know it feels weird, but that's what we have. Whoops. Let's try to fix that. Okay, so here is the point where you have to figure out what those numerators are going to be. Now, the first one, x squared plus 9, is like the x squared plus 1 that I sort of was talking about on the last example, right? So my numerator needs to be a linear expression. So what could I write it as? Yeah, ax plus b. And although my denominator on the second expression is a power of 4, it's one of these repeats. So I don't need a third power expression up there. I can use another linear one, just like the same linear one that I just now used. So cx plus d, right? Are we good with that so far? All right. So we're going to go ahead and combine these guys back together, and how are we going to do that? Common denominator, but that's actually really friendly because there's only one of them that doesn't have the denominator I want, right? So the first denominator needs to be multiplied by what? X squared plus 9. Now, of course, in doing that, you have to remember that that first numerator gets to be FOILed out, right? First outer inner last. So I've got ax times x squared, which gives me ax cubed. My outside terms are ax times 9, so I've got 9ax. My inside terms are b and x squared, so I've got bx squared. And then the last terms are b and 9, so I've got 9b. And then I still have that cx plus d from the very end. Okay. I know it looks like it's really messy. I promise it's going to clean up before you know it. So take a look at what we have here besides the mess. All of this has to equal what? Whoops, hang on, let's try that again. I'll just leave it there. Has to equal, what was that? X squared minus x. You guys are really quiet people. Minus x plus 9. Is that what it is? Okay, so let's collect terms. The first term that I notice that I've got on one side is I've got an x cubed. And there is an ax cubed on the left, so there's an a. What cubed term is happening on the right? 0. There isn't any, and that's actually great. I'd love it if my numbers were 0 because that makes them easy to work with, right? Sure. Let's do x squared terms. What x squared terms do we have? Just b and 1 on the right, so b is 1. Hey, we're just trucking right along. How about my x terms? What x terms do I have? 9ax, so 9a, and c, and what does it have to equal? -1, but notice if a is 0, which it is, what is c? C is 1, so I don't normally solve as I go, but this one seems awfully nice, so c is -1. I still got to figure out what d is, and I need my constant terms here at the end. So what constant terms do I have? 9b, good, and d, and they have to equal 9. And you know that b is 1. So what's d? It's 0. So it couldn't get much better than these values, to be perfectly honest. These are pretty nice. I've got a couple of zeros in there, and I've got a 1 and a -1. Those are nice values to work with, right? So take a look over here, and we can actually work with this to simplify pretty quickly. So this is the integral of, again, a was 0. What was b? Was 1. So this is 1 over x squared plus 9 dx plus. Now I've got an integral. What was c? -1, so this is -x. And what was d? 0. So it's just -x over x squared plus 9. All of that, though, squared. Of course, chosen on purpose because you see some other things happening now. That first one, 1 over x squared plus 9, do you know what that is? It's arctangent. Yes, it is. That's an arctangent. It's an arctangent where the value here at the back is a 3 squared, right? So this is x squared plus 3 squared. So if you were to take a look at your arctangent integration rule, that one right there, this would actually tell you that it's 1 over that value that's squared, so it's 1 over 3 arctangent of x over 3. So that's the first piece. And as unfriendly as you might think that that looks, the second piece actually requires more work. Because what happens with the second piece that we're working with here? The bottom squared, isn't it? You guys told me a little while ago you like u substitution. Can you use it? What could u be? X squared plus 9. Because what is x squared plus 9's derivative? 2x dx. And that's not exactly the numerator, but it's close enough, isn't it? So I can divide both sides by 2. The negative from here can come out in front. So this is going to be, okay, so I realize I'm down here now going on. This is negative integral, 1/2 the integral of what? Well, the 2x dx, these cancel, so the x dx is going to get replaced right here with du. That's my du. 1 over u squared, or I could write that as u to the negative 2, right? Yeah? Okay, great. All right, so we're almost done, and I don't want to switch slides, so I'm going to keep going on this one. I've got 1/3 arctangent of x over 3, and I've got minus 1/2. What's the antiderivative of u to the negative 2? We've already done this one today. U to the negative 1 over negative 1, and u is x squared plus 9, right? So I've got, well, let me write it. U to the negative 1 over negative 1. And my plus c. I'm going to have to go to another slide. It's okay. And it's just going to be a bright white one. All right. So as we said, here's my arctangent of x over 3. The negative and the negative are going to be a positive, so I have positive 1/2 here, or 1 over 2. What's my u value again? X squared plus 9. In the denominator, yeah? And then plus c at the end. And that's the result after all of the work. Any questions on that?